Well, hello Math 160 students. I just wanted to follow up with you after our class today where we did a few examples of related rates with maybe one more example that we could practice on. These types of problems come in all shapes and varieties, and they can be challenging sometimes. I know they were for me when I first learned the material, and I thought it'd be good to show you one more example. The more practice that we get with these things, the better. And this one is a little bit different than the ones that I did in class in that it really isn't based on a whole lot of trigonometry. So it's more based on just some concept from physics that is sort of a well-known concept. In fact, I realize right now I forgot to draw my figure up here. I have two resistors, R1 and R2, connected in parallel. So this is just an electric circuit. Let me just draw the picture here. So you have a couple of resistors. This is R1 and this is R2 right here. Okay? And the total resistance of this circuit, by the way, resistance is measured in ohms. If you haven't taken a lot of physics, it's okay because they give you the formula in the problem of how the total resistance is a function of the individual resistors that are in that picture up there. But it's a little deceptive because you might look at the picture and think that that has a lot to do with setting up this problem. A lot of related rates problems involve geometry or trigonometry and various relationships that way. And you might think that the picture is crucial here. Usually though, right, the picture is the thing that gives you the geometric relationship between the functions that you're looking at in the problem. In this case, the relationship is given to you in the question itself. So the total resistance R is given by its reciprocal being equal to the sums of the reciprocals of the individual resistances. Okay? So we're going to just use that for free. So we don't really need step 1, which is to draw the picture, or step 2, which is to label the picture. We can kind of move past that and focus more on the remaining steps of the related rates process. So let's just work through this. The last part of the question here, in case you can't read it totally clearly, is just suppose that R1 and R2 are increasing at rates of 0.3 ohms per second and 0.2 ohms per second. The question is then asking how fast is R changing when R1 is equal to 80 and R2 is equal to 100. Okay, so there's a lot of words here, but what we are trying to find is the third step of our process. So let's write down what is it that we would like to find in this example. How fast is R changing, right? Well, that is just precisely the derivative of R with respect to time. Okay? And what we know, the things that we are given, because that's the next step, step 4 of the process, is to write down what do you already know. Well, there's a lot of stuff here that you are given, right? You know that the rate of change of R1 with respect to time is 0.3, and the rate of change of R2 with respect to time is 0.2. Okay? And then we have R1 and R2. Those values are also known. They're right down here. Let me just write those down as well. R1 is 80 and R2 is 100. Okay? So normally we would use geometry to write down the relationship between R, R1, and R2, but that's been done for us right here. So we don't have to bother with that part. We can go straight to taking the chain rule to differentiate this equation. So let's do that. These are just -1 powers of those various resistors. So we can just use the power rule to differentiate these things. So we're going to get negative 1 over R squared times dr dt, that's just the chain rule, equals -1 over R1 squared times dr1 dt, and then minus 1 over R2 squared dr2 dt. Okay, I just basically did the same thing to all three fractions there. I just differentiated them completely. Okay, and the thing we're trying to find is right here. And everything on the right-hand side of the equation we already know, right? We know the rate of change of R1 and of R2. And we know what R1 is, we know what R2 is. We don't yet know what R is. I guess maybe we should figure that out. But we can find R by using this equation. Okay, so let's write this down. We know that 1 over R would be 1 over R1, which was given as 80, plus 1 over R2, which was given as 100. Okay? If you find a common denominator of 400 out of that, you're going to see that it's basically 5 plus 4. Going kind of quickly through the basic math here. But that's 9 over 400. Okay, good. So R is 400 over 9. That was one of the other numbers that we still needed to find. So let me, I'm just going to erase right here so that I can finish this problem off. I'm going to start just plugging these numbers in. So 1 over R squared, let's see, that's just going to be, and we have a negative. So that's negative of, well, it's 9 over 400 squared times dr dt. Okay? And then on the right-hand side, I have negative of 1 over 80 squared, and that's times dr1 dt. Oh, let's just put in what that is. dr1 dt was 0.3. Okay, and then minus 1 over 100 squared times dr2 dt, which is 0.2. So this is getting us into pretty good shape. All right, we can just about finish off the problem at this point. Let me I'll erase the picture. We never really needed that anyway. And of course I have minus signs that I can change to positives if I want to. That'd be one thing we could do. And then moving 400 over 9 squared to the other side would maybe make sense because we want to get dr dt by itself. So I'll do that. 400 over 9 quantity squared. And the rest of this is just, I don't even have my calculator handy, so I'm not even going to get a final answer for you here, but you guys can certainly do this. Basically, we just calculate this value, and then we have to multiply it by 400 squared over 9 squared. Okay, so this is just a quick little calculation that you can do. I won't bother you with that part of it, but hopefully the steps are clear here. The difference between this example and the ones that we did in class is that the picture really is not relevant. In some ways this is easier because they just gave you the formula, which is independent of really using the picture at all. The rest of it though, putting down what you want to find, what you know, and taking the using the chain rule to differentiate the expression, and then plugging in the values. That part of it all works the same. So hopefully this is clear. Just wanted to give you another example that's of a slightly different nature. If there's any questions about this example or any of the group work or any of the homework that you're going to be doing, certainly feel free to ask me. Like I told you at the beginning, this can be sometimes a section that you have to practice quite a little bit, and I'm more than happy to help you out with that. So hopefully this is all clear. I appreciate it. Thank you guys very much.